Good morning. In today's session, we will see the Norton's theorem. The objective is to define the Norton's theorem, and the second objective is to verify the Norton's theorem for the given circuit. See, basic purpose of using different theorems is to simplify our calculations. So by using some equivalent circuits, one can replace a complicated network to a simple network. So this Norton's theorem states us that any complicated network which consists of different energy sources and circuit elements, when connected between two terminals, say A and B, can be replaced with a simple equivalent circuit. That equivalent circuit consisting of a current source in parallel with a resistance. Okay, so whatever complicated network is there, any complicated network that can be replaced with a current source. Okay, and what is the value of that current source is there, that I will write as ISC. And a resistance is connected in parallel with this current source, and this resistance is nothing but Rn. Okay, now what are the initial terminals are there, A and B? Those initial terminals are retained, and in the last step I can reconnect the load. That means whatever the load is removed initially, that load we have to connect. So basic purpose is to find out a current flowing through load resistance of any complicated circuit. So that circuit I am replacing with this circuit, which consists of ISC in parallel with Rn. So whatever the ISC is there, this ISC is the short circuit current. And meaning of short circuit current is whatever the given load part is there, load circuitry is there, that load circuitry I have to short, and a current flowing through that short is nothing but the ISC. Now whatever this Rn is there, that Rn is the Norton's equivalent resistance. And the procedure for finding this Rn is remove the load, just open it, disconnect it, remove all the sources. If voltage source is there, short it. If the current source is there, open it, and measure the resistance looking back into the network. That is your Rn. Then draw the equivalent circuit where ISC is in parallel with Rn. So this is the Norton's equivalent circuit. So finally, whatever the load is there, that I have to connect. So if I want the current flowing through a load resistance, say IL, now for this simple circuit, I can use current divider rule. See, these two branches are parallel and the current source is there. So current flowing through RL is nothing but the IL, and that is given by opposite resistance Rn divided by Rn plus RL into ISC. So this is your Norton's theorem. Any complicated circuit can be replaced by a simple current source with ISC as the value and Rn as the internal resistance of that current source. Now in a second objective, we have to verify this Norton's theorem. So to verify the Norton's theorem, the procedure that we will follow is, let us take this simple circuit. Okay, so let us define this as the load. Okay, that means 20 ohm is the load resistance. So how to calculate I20 ohm using a Norton's theorem? And this answer I will check by using some another method, and if the both answers gets matched, then theorem is verified. Okay, so what are the step number 1 is there? See, let us calculate ISC. So my first step is calculation of ISC. What is ISC? Short circuit current. So procedure here is, whatever the load circuitry is there, just replace by short circuit and find out current flowing through short. So when I'm putting a wire across this RL practically, then that load gets shorted. That means your circuit is now simply like this one. So this is short, that load resistance gets shorted. Then you have 10 ohm here, here 15 ohm, here 5 ohm, and here a current source of value 5 ampere. And we have to calculate how much is the current flowing through this short circuit, that is your ISC. Are you getting this one? So this 15 and 10 are in series. That will result to 25 ohm, a single resistance. And across that 25 ohm, a short is placed. Means your situation is like this one. Here you have 25 ohm and here you have placed the wire. So what is the equivalent of this one? Equivalent of these two is nothing but short circuit itself, because meaning of the short circuit is a resistance of 0 ohm. Okay, so this 0 ohm is in parallel with 25. So if you calculate this parallel combination, 0 into 25 divided by 0 plus 25, so that becomes 0. Okay, that means the concept is, when you are putting a wire, putting a short across some network, across some resistance, what is the final value is there, that is 0. Okay, that means now if I calculate this current, see this gets shorted. That means as if no connection is there. So this 5 ampere current will flow through short itself. There will be no current flowing through 15 and 25. So your ISC in this case is nothing but 5 ampere. So in step number 2, I have to calculate Rn. So it is calculation of Norton's equivalent resistance. So procedure here is, whatever the load resistance is there, that you have to remove. Whatever the sources are there, those sources are also removed. So if current source is there, open it. If voltage source is there, short it. And measure the resistance between those two terminals, wherefrom you have removed the load. Okay, so your circuit for this calculation will be like this one. So this is A terminal, this is B terminal, RL is disconnected. Now what are the current source is there? Current source we have removed, and the resistance of 10 ohm is here, 15 ohm is here, and this is 5 ohm. And this resistance between A and B is nothing but Rn, Norton's equivalent resistance. So if you look at the circuit from terminal A to the left of terminal A, you have 5 ohm, but another terminal of 5 ohm is nowhere connected in the circuit. Okay, that means as if this resistance is removed. Again, this connection, this point is not connected anywhere, that means this is removed. So when you are measuring Rn between terminals A and B, that is 15 and 10 that are in series. Okay, so that means your Rn is nothing but 15 plus 10, that is 25 ohm. So this is the first major calculation, this is the second calculation. Now when I am going for the last one, step 3, now what is step 3? You have to draw a Norton's equivalent circuit. Okay, so it is a Norton's equivalent circuit. Now whatever that circuit is there, it includes a current source of value ISC in parallel with a resistance Rn. This is between terminals A and B, and finally I will connect the load resistance RL. So the values we got here, 5 ampere, this Rn value is 25 ohm and the load value is 20 ohm. We have defined the task like this: when this 20 ohm is the load resistance, so I have to calculate a current flowing through 20 ohm. So this current, and there we have RL. So that calculation results to RL, which is nothing but I 20 ohm, that is current flowing through 20 ohm is, see, these two resistances are in parallel across a current source. The simplest way is to use current divider rule. So what is the rule? Opposite resistance 25 divided by 25 plus 20 multiplied by a current source, it is 5 ampere. So it is 125 divided by 45. So just do the calculation and tell me the answer. Yes, it is 2.77 ampere. Okay, that means current flowing through this 20 ohm using Norton's theorem is 2.77 ampere. That means in the first objective we have followed the procedure of Norton's theorem. In a second objective we have to verify this theorem, and in order to verify this theorem, again I have to calculate current flowing through 20 ohm using some another method. So if I use, say, node analysis method, so in node analysis I have to find out nodal voltage, and by knowing the nodal voltage and resistance I can calculate the current flowing through required resistance. Okay, so whatever the circuit is there, this is the given circuit. So here it is 5 ampere, this is 20 ohm, and then you have 15 ohm, 10 ohm and 5 ohm. Okay, so we'll define the node. So this is one node. So if I write this node is, say, A, node A. This is another node, say node B. I will define the nodal voltage as VA, here nodal voltage VB. One node I will take at a reference potential of 0 volt. Okay, then I will assume the different currents. Say it is I1, I2 and I3. So here I1 is essentially 5 ampere. So in the next step I will apply KCL at node A. That means in order to find out nodal voltage, we will apply KCL at node A. Your KCL is incoming current is equal to the sum of outgoing currents. That is I1 is equal to I2 plus I3. So I1 is 5 ampere, that is equal to, now this current I2, so here potential is VA, whereas the reference potential is 0 divided by 20 plus I3 current is VA minus 0 divided by, these two are in series, so it is 15 plus 10. Okay, that means by using nodal analysis method we have applied KCL and we got this equation. Now this equation how to simplify to find out the nodal voltage. Okay, so just do this calculation. Now whatever the nodal voltage is there, after simplifying this equation, you will get the value 55.55 volts. Let's check it. It is, yes, 55.55 volts. So finally I need I20, that is the required current flowing through a 20 ohm. So I want this current, so it is VA minus 0 divided by 20. So 55.55 divided by 20, if you calculate that, once again your answer will be 2.77 ampere. Check it. So this current, which is I20 using Norton's theorem, and this current, which is again current flowing through 20 ohm using node analysis method. Since both the currents are equal, it means we have verified the Norton's theorem. So any complicated network, here we have taken a simple network. If you use any complicated network, if you follow the steps, you will get one answer for load current. Again, that complicated network you have to analyze by using another method and find out the current. And what you have to show, both the currents are equal. If you are getting both the currents equal, your Norton's theorem is verified. Thank you.